Hi everyone, welcome to this video. So me and my group members will be doing a science presentation on space exploration. So if you want to gain more knowledge about it, just sit back and relax. So without further ado, we'll start our presentation now. Wait, let me introduce my group members. So first will be me. I'm Gwen Eng Singni from Tree Crystal and I'm the leader of this project.
Hi, I am Chen Ziha.
Hi, I'm Dinuka.
Hi, I am Shannon.
Hi, I'm Celine. So this is the index for today's presentation. So let's start our presentation with the history of solar system models. Let's talk about Ptolemy. Claudius Ptolemy, 90 to 168 AD, was a mathematician, astronomer, geographer, and astrologer who wrote about a dozen scientific treatises. He built the geocentric model with Earth at the center and circular orbits. Ptolemy attempted to resolve the planetary motion dilemma in which the observations were not consistent with the perfect circular orbits of the bodies. Ptolemy proposed a complex motion called epicycles. Epicycles are described as an orbit within an orbit. For example, looking at Venus, Ptolemy claimed that it orbits the Earth, and as it orbits the Earth, it also orbits the original orbit. Ptolemy emphasized that the epicycle motion does not apply to the Sun. This model, where Earth is positioned at the center of the solar system, is known as the geocentric model. So for geocentric model, geo means Earth, centric means center. Earth is at the center of the solar system. Earth is stationary and all the objects such as the Sun and other planets revolve around Earth in circular orbits. So next, we'll talk about Copernicus. Nicolaus Copernicus, 19 February 1473 to 24th May 1543, was a Polish astronomer, mathematician, economist, and doctor. He built the heliocentric model with the Sun at the center and circular orbits. Copernicus' great work is called On the Revolutions of Celestial Spheres. In it, he proposed essentially the modern model of the solar system where the Earth and the other planets all circle the Sun, while the Moon circles around the Earth. Copernicus noted that for the stars to orbit the Earth, they'd have to be traveling at the enormous speed. Far simpler, he thought, for the Earth to rotate on its axis once every day and that each year represents one orbit of the Earth around the Sun. And that's the modern view. For heliocentric model, helio means sun, centric means center. The Sun is at the center of the solar system. Earth rotates on its axis and revolves around the Sun in a circular orbit. Then we'll talk about the Kepler. Johannes Kepler, 27 December 1571 to 15 November 1630, was a German mathematician, astronomer, astrologer, and natural philosopher. He's a key figure in the 17th century scientific revolution, best known for his laws of planetary motion and his books Astronomia Nova, Harmonices Mundi, and Epitome Astronomiae Copernicanae. He also modified the heliocentric model with the Sun at one common focal point on the elliptical orbits of the planets according to Kepler's law. Since completing the Astronomia Nova, Kepler had intended to compose an astronomy textbook that would cover all the fundamentals of heliocentric astronomy. Kepler spent the next several years working on what would become Epitome Astronomiae Copernicanae, which is the epitome of Copernican astronomy. Despite its title, which merely hints at heliocentrism, the epitome is less about Copernicus' work and more about Kepler's own astronomical system. So this is the picture of modified heliocentral model according to Kepler's law. Then we'll talk about the similarities and differences between the solar system models. First, we'll talk about the similarities and differences between models built by Ptolemy and Copernicus. Their similarities are, in the solar system models built by Ptolemy and Copernicus, Earth or the Sun revolve in orbits. Whereas, the differences, in the solar system model built by Ptolemy, Earth is at the center of the orbit, whereas in the solar system model built by Copernicus, the Sun is at the center of Earth's orbit. Next, we'll talk about similarities and differences between models built by Copernicus and Kepler. Their similarities are, The solar system models built by Copernicus and Kepler are heliocentric models, whereas there are differences. In the solar system model built by Copernicus, Earth and planets revolve in circular orbits, whereas in the solar system model built by Kepler, Earth and the planets revolve in elliptical orbits. Lastly will be the similarities and differences between models built by Ptolemy and Kepler. Their similarities are, in the solar system models built by Ptolemy and Kepler, both of the other planets orbit in the same way. Differences: in the solar system model built by Ptolemy, it denotes that all objects include the Sun, Moon, and other planets revolve around the Earth, whereas in the solar system model built by Kepler, it denotes that all other planets include Earth, Moon, and stars revolve around the Sun.
First, I would like to explain the constructions of a rocket. Modern space rockets have main engines powered by a liquid fuel and liquid oxygen that are pumped in from huge tanks. Next is the functions of rockets. A rocket is a projectile that spacecraft, aircraft, or other vehicles use to obtain thrust from a rocket engine. Rocket engines work by action and reaction and push rockets forward simply by expelling their exhaust in the opposite direction at high speed, and can therefore work in the vacuum of space. Next is the importance. Rockets are used to launch satellites and space shuttles into space and also provide the necessary energy for human space travel. They have changed the world completely and have given us new eyes for the universe.
T-minus 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Construction of satellite. The main component of the satellite consists of the communication system, which includes the antennas and transponder that receive and retransmit signal, the power system, which includes the solar panels that provide power, and the propulsion system, which includes the rocket that propels the satellite. The function of the satellite is to collect information about outer space and for telecommunication and weather forecast purposes. Weather satellite. A weather satellite is used for forecast the weather and climate of the Earth. The information received from the satellite, such as the cloud patterns, wind directions, temperature, and pressure in the Earth's atmosphere, help meteorologists to predict weather conditions and climate changes. Telecommunications. A communication satellite is used to send information by transmitting signal through radios, television, telephones, telesource, the internet, and other communication devices. Navigation. The navigation satellite is used for aid navigation of sea and air traffic. It is also used in determining the position of ships and aircrafts. Military purposes. Satellites are used by the military for security and defense. Satellites are also used to spy on other countries. They provide intelligence on the military activity of foreign countries. Importance of satellite. In communications, they allow us to make cellular phone calls from long distances, global position system GPS, relay weather conditions and forecasts. In transportation, satellite communications will enable transport hubs to monitor the progress of journey and offer real-time route updates. Satellite information will also allow from the monitoring of sea, land, and air pollution. The government use them to spy on other countries in order to protect us. They're used for space research, which includes the SOHO satellite that observes the sun and provide us with early warning of upcoming solar flares. Malaysia's first satellite is ChongSat-1. The satellite developed through the technology transfer and training program between Astronautic Technology Sdn Bhd, ATSB Malaysia, and Surrey Satellite Technology Ltd, United Kingdom. ChongSat-1 mission objective is collection of imagery for environmental and meteorological use, space science, digital SNF, stay and forward communications, amateur radio access, and technology demonstration.
The constructions of space probes. A space probe is an unplugged unmanned device sent to explore space and gather scientific information. It is launched from Earth with a set of scientific instruments and tools used to study the atmosphere and composition of space and other planets, moons, or celestial bodies. Furthermore, space probes may operate far out in space, or it may orbit or land on a planet or a moon. Most probes transmit data from space by radio. There are different types of space probes because they collect different science information about very different environment. The functions of space probes. Space probes have visited the moon, asteroids, comets, and every planet in the solar system. There are three types of space probes: interplanetary, orbiters, and landers. The importance of space probes. Space probes are made to conduct science experiments. They do not have people on them. Space probes have helped scientists get information about our solar system. Most probes are not designed to return to Earth. Some have landed on other planets. There are even some space probes that go into orbit around other planets and study them for a long time. The information they gather is used to help us understand the weather and other changes which happens on planets other than the Earth. This information is important in helping to other space missions such as ones to the Mars and to Saturn.
9, 8, 7, 6, 5, 4, 3, 2, 1. Go New Horizons! Go New Horizons! Woo-hoo!
joy, relief, and celebration. Billions of kilometers from Earth, humanity has encountered a mysterious icy rock 4.5 billion years old.
We're here to tell you that last night, overnight, the United States spacecraft New Horizons conducted the farthest exploration in the history of humankind, and did so spectacularly. Thousands of operations on board the spacecraft had to work correctly in order for us to be able to tell you this, and now we know that it all did.
Scientists feared the New Horizons spacecraft could have been seriously damaged by even the smallest particle, but luckily that didn't happen. And after being out of contact for 10 hours, they received a radio signal that the spacecraft had survived its flyby of the cosmic body named Ultima Thule. Flying at 51,000 kilometers per hour, the spacecraft snapped thousands of photographs of the dark icy space rock as it sped past it on the outer edge of the solar system. Over the coming months, it will send those images back to NASA.
Overnight tonight, the science team will be analyzing the first high-resolution images, which we'll be able to show you tomorrow. Now, the image that I'm about to show you is the best image of Ultima that we got pre-flyby, and it's okay to laugh, but it's better than the one we had yesterday. There it is. Meet Ultima.
Ultima Thule lies around 6.5 billion kilometers from Earth, near the edge of the solar system in the Kuiper Belt. That region consists of many dwarf planets, space rocks, and icy debris left over from the days when the solar system was first forming. New Horizons zoomed past Ultima 3.5 years after its spectacular brush with Pluto. It took 6 hours for the radio signals from New Horizons to reach Earth, and it will take nearly 2 years for all of its data to be beamed back. Ultima is shaped like a peanut, but these scientists say it'll soon be viewed as an entirely new world.
So let's start with constructions of remote sensing. Remote sensing is the process of acquiring information, detecting, analyzing, monitoring the physical characteristic of an area by recording its emitted radiation energy without having any physical with the object. The functions of remote sensing is used to analyze the condition of real roads, creating a base map for visual reference, collecting Earth pictures from space, controlling forest fires, detecting land use and land cover, estimating forest supplies, and to observe climate change. The importance of remote sensing. With the help of remote sensing, humans are able to discover large areas in outer space that are inaccessible to humans. Other than that, remote sensing can characterize natural features of physical objects on the ground and objects on a systematic basis and monitor their changes over time.
To talk to you today about the classification of remote sensing. Remote sensing is classified into two: active and passive. So what is active? Active is when the sensor embodies within itself the source of illumination. We had cameras which used to have a built-in flash on them. So the moment you clicked a picture, the flash would fire, the light from the flash would get reflected from the object, and the camera would record a picture. So in this case, the camera is also carrying the source of illumination. I have put it rather very simply. When it comes to sensu stricto, active remote sensing, we understand active remote sensing as in radar, because when you have a satellite which is equipped with a radar transponder, it's sending out radar waves or radio waves which bounce off from the Earth's surface. The time required for the waves to hit the Earth's surface and be recorded by sensors on the satellite is what is utilized for making an image. It's an excellent example of active remote sensing. What's happening right now is remote sensing. There's a digital camera in front of me. It's imaging me or collecting data or photographing me only because I'm being illuminated by two spotlights. This is very similar to how sun illuminates the Earth and reflectance from the Earth's surface is collected by the satellite. So the sensor itself is not having a source of illuminating the ground surface or the object which it is imaging. The sun, earth, and satellite sensor example is a classic to understand passive remote sensing. It's passive because the sensor is not carrying its own source of energy. Just like right now, this standalone camera does not have its own illumination source. What I've just told you, in very simple terms, is the basic classification of the technology of remote sensing. So with that, we've defined very precisely the two types of remote sensing. Thank you.
The construction of telescope is, telescope are lenses that work by using curved mirrors to gather and focus light from the night sky. The bigger the mirror or lenses, the more light the telescope can gather. Astronomers often use eyepieces, which are usually sold along with a telescope to maximize its purpose. The function of the telescope is to collect faint light from an astronomical source to focus all the light into a point or an image and to magnify the image. The importance of telescope is used to form magnified image of distant objects. It provides means of collecting and analyzing radiation from celestial objects, even those in the far reach of the universe.
Seconds before liftoff, the Ariane 5's liquid-fueled engine comes to full power, followed by the ignition of the two solid rockets. We have liftoff. The Webb telescope is finally on its way, the result of years of study and development by thousands of team members in the United States, Canada, and Europe. Webb spacecraft ascends nearly vertically through the heavy lower atmosphere of Earth. As the rocket reaches maximum acceleration, the spent solid rocket motors are jettisoned safely into the Atlantic Ocean. Reaching the upper atmosphere where protection is no longer needed, the payload fairing is jettisoned and falls away. Accelerating through the atmosphere, the Ariane 5 rocket's first stage expends its fuel and shuts down. The empty first stage then separates from the upper stage. After first stage separation and before second stage ignition, the Webb telescope has a slightly downward trajectory as it speeds over the Atlantic Ocean. The upper stage motor ignites and the ascent to L2 resumes, never again to be interrupted. The exposed telescope is delicate and must be protected from the sun's fierce heat. To avoid overheating and damage, a carefully designed series of oscillations are performed that provide the necessary protection. The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit.
I will talk about remote sensing technology used in agriculture, geology, disaster management, and defense, and also their importance. Number 1. Agriculture. The first thing for agriculture is identifying crop conditions. Satellite imaginary and normalized difference vegetation index, or NDVI technologies, are used in order to monitor global food supplies. Besides that, determining the soil moisture content, active and passive sensors of a satellite in space are used in order to determine soil moisture content. Many earth sciences such as water cycle, flood, and drought are based on the content of soil moisture. Number 2. Geology. It was used in the geological sciences as a data acquisition method, complementary to field observation. Remote sensing is conducted via detection of electromagnetic radiation by sensors. The radiation can be naturally sourced or produced by machines and reflected off of the Earth's surface. The two-way travel time of radiation from and back to the sensor can calculate the distance in active remote sensing systems. For example, interferometric synthetic aperture radar. Remote sensing data can help studies involving geological mapping, geological hazards, and economic geology. These geological studies commonly employ a multitude of tools classified according to short to long wavelengths of the electromagnetic radiation which various instruments are sensitive to. Number 3. Disaster management. First of all, remote sensing provides a database from which the evidence left behind by disasters that have occurred before can be interpreted and combined with other information to arrive at hazard maps, indicating which areas are potentially dangerous. Many types of disasters such as floods, drought, cyclones, volcanic eruptions with certain precursors, the satellites can detect the early stages of these events as anomalized in the time series. Last but not least, 4. Defense. The advent of remote sensing technology has provided essential intelligence information to defense forces. Spy satellites constantly acquire high-resolution satellite data in peacetime to monitor the development and acquisition of modern warfare gadgets by the enemy forces. These are brought to the notice of international agencies coordinating the prevention of nuclear energy for destructive purposes. The use of remote sensing data combined with ground information provides a common platform for analyzing ground situations in time of war. The incorporation of satellites providing high-resolution images in the present era enhances the ability of GIS to provide more accurate and current information to the military operations.
Hi, I'm Emerald Robinson, and in this What Is video, we'll try to answer the question, what is remote sensing? Remote sensing is any technique used to gather information about an object that does not require touching the object. Remote sensing can be done with devices either on the ground or on ships, planes, or even satellites. There are two parts to remote sensing. First, devices record radiation like light or heat from an object or area. And second, this data is analyzed to determine what it means. For simplicity, we can divide all of the devices used in remote sensing into two groups. In passive remote sensing, technology is used to record an object's natural radiation. An infrared camera on a tripod that records heat coming from a rock formation or an airplane flying over a rainforest that registers the sunlight reflected from the forest's canopy are examples of passive remote sensing. Active remote sensing takes place when a device sends out a signal in order to gather information about an object. A ship that sends sonar waves to scan the ocean floor uses active remote sensing, as do satellites that monitor hurricanes. Although you may not realize it, you benefit from the results of remote sensing almost every day. Meteorologists count on it to help generate weather forecasts. Police use it to catch speeding cars, and geologists use it to create maps of all kinds. A special type of remote sensing called light detection and ranging, or LiDAR, is a type of active remote sensing that uses lasers. LiDAR is used by everyone from farmers to help fertilize their crops to engineers who use it to help them survey the land. In fact, you're using a type of passive remote sensing right now. Human eyes and ears capture light and sound waves and allow us to detect information about an object without even touching it.
The importance of space exploration in a local and global context. In the global context, humans carry out space exploration to help address fundamental questions about our place in the universe and the history of our solar system. Through addressing the challenges related to human space exploration, we expand technology, create new industries, and help to foster a peaceful connection with other nations. For example, space exploration enables scientists to look for another habitable planet because Earth may be destroyed due to collision with an asteroid. In the local context, space exploration inspires children or younger generations to study science, which is valuable than other expenditures such as warfare. In continuation to that, it could also help to improve our day-to-day lives by enhancing safety on Earth and creating scientific and technical jobs. Space explorations has helped in advancements in the fields of health and medicine, transportation, public safety, consumer goods, energy and environment, information technology, and industrial productivity.
Last but not least is development in space exploration. On the 11th century, Chinese people invented gunpowder and used primitive rockets in battles. On 1609, the first telescope was used in the field of astronomy by Galileo Galilei. Next, on 1957, the first satellite USSR Sputnik 1 was launched into space. Continuing on 1961, Yuri Gagarin is known as the first human to orbit Earth aboard USSR Vostok 1. Then on 1969, Neil Armstrong became the first human to set foot on the moon. The rocket used was the US Apollo 11. On 1973, we had our first Jupiter flyby by the US Pioneer 10, followed by the year 1981, the first flight of US Space Shuttle Columbia. Next, on 1990, the US launched Hubble Space Telescope from Space Shuttle Discovery. Continuing by the year of 2000, Malaysia's first microsatellite, Tiongsan-1, was launched into space. Then on 2002, the National Space Agency, Agensi Angkasa Negara, is established. It ends on 2011 when the construction of International Space Station, ISS, is finally completed.
When we see the Earth from space, we see ourselves as a whole. With a compelling message, one planet, one human race.
We opened hatch in space. We were opening hatch on the Earth. And we're in the history of man.
We are here together. We need to live together with tolerance and respect. We must become global citizens.
Okay, so we have now came to end our presentation, but before that, we will debate the issue of continual space exploration in the local and global context. The main topic we will debate is space exploration inspire children to study science or other fields of science can also inspire children to study science. So we will now listen to Liluka and Gwen's conversation. This debate is only for this project, no harm meant.
From my point of view, I think that space exploration might not be only inspiring to adults to study science, but children as well. By studying the solar system, for example, has brought us insights into such phenomena such as gravity, the magnetosphere, and atmosphere in other planets. In addition, the excitement generated by space exploration attracts young people to careers in science, technology, engineering, mathematics, helping to build global capacity for scientific and technological innovation.
No! Space exploration is a waste of resources. Instead of decreasing resources by space travel and such, we must deal with problems on Earth first. Why bother spending all this money on exploring space when we could be helping our own planet that us humans live on? Space exploration is a waste of money and a waste of time. Science may well give us good things.
However, I think that space exploration fuels our children's curiosity and imagination. Role models like astronauts inspire students to dream and consequently achieve their goals. Many astronauts, engineers, scientists, and innovators remember watching the moon landing as kids, being motivated to work towards their dreams.
I disagree. The needs of humanity should always come first. While there are people on Earth who needs help, there should be help. Rather than seeing money spent on sending robots onto other planets, humanity is the #1 priority. Keeping the human race alive is a necessity. Alternatively, space exploration is a desire. If we put our desires before our needs, then everyone loses out on a better standard of living. Sure, it's great that NASA can elevate technology to the next level time and time again. So why not make technology that directly benefits us? And as there are millions around the world who are starving to death, When people spend more and more money on space technology, they should realize they are the killers.
But you must know that space exploration tells us about the fascinating phenomena and history happening in outer space, a place not just anyone has access to. From stories of space exploration to working under extreme pressure, astronauts share an inspiring experience of heroism and determination that can captivate an audience from all walks of life.
But why take so much time and money to learn about Mars or any other planets when we know so little about our own? We should learn more about the Earth and the ocean before wasting time and money on space exploration.
In conclusion, I can say that some points are wrong, some points are right, and some are a bit of both.
We both should respect each other's view, and that concludes our discussion. I'm Gwen Eung Singni from Tree Crystal.
Hi, I'm Dinuka.
Hi, I am Chin Zi Han.
Hi, I am Shannon.
Hi, I'm Celine. Last but not least, all of us would like to thank our science teacher, Cikgu Rozana.
Thank you, Cikgu Rozana.
Thank you, Cikgu Rozana. Thank you, Cikgu Rozana.
We may not always say it, but we mean it whenever we say it. Thank you, teacher, for all the extra efforts you make to help us grow and challenges you encourage us to face to help us become who we are. You are not only our teacher, you are our friend, authority, and guide, all rolled into one person. We will always be grateful to you for your support and kindness. So that will be ending our presentation. Thank you everyone for watching this video. Hope you guys like our presentation just now. Thank you. Bye.